This is part of the lecture for multivariable calculus, and we are going to talk about vectors. What is a vector and how to represent a vector? And we are going to talk about simple algebraic operations on vectors, like adding two vectors, scalar multiplications of vectors, magnitude of vectors, and unit vectors. So let me start. Vector is a quantity which has a direction, and magnitude, or we call it length. Okay, so some quantities like force in physics, or velocity, or displacement. So all of them, we can represent all of them by a vector. And a vector has a direction and has a magnitude. So these two are the most important factors of a vector. So we're going to show vectors by a line segment with an arrow. And this part is called the tip, or the terminal point, and this point in here is the tail, or the initial point. We represent vectors by an arrow in math books. So we're gonna show it like that. For example, the vector v with an arrow on top, or we show it by AB. So what is we? Just assume that this is a vector v, and the same vector, I'm gonna copy it, I'm gonna paste it, okay, but I'm gonna use 2 points A and B. And also we can use another 2 points C and D in some other place. Okay, but as I said before, just the direction of the vector is important and its length. So these two factors identify a vector. So where we draw it, it doesn't matter. Let me write it. Where we draw it does not matter. Does not matter. Okay. We can also express vectors by components, in coordinate system. So assume that this is x-axis, this is y-axis, and this is z-axis. And I'm gonna have a vector v starting at the origin, and I'm gonna show by its component a, b, c. What are a, b, c? So v goes a unit along x-axis, it goes b units along y-axis, and it goes c units along z-axis. Okay, and so A, B, and then C would be exactly the coordinates of this point in here. So starting at the origin, we can show this component to express the vector V. Let's look at one example. For example, I'm starting at the point A with the coordinates 1, 2, and 3, and I go to the point B with the coordinates 5, 8, and 11, and then I have this vector. This vector is the vector AB, and to write the components of this vector, I need to subtract the component of the endpoint minus the first point. So it would be 5 minus 1, 8 minus 2, and 11 minus 3. Okay, so the vector AB has the components 4, 6, and 8. Okay, very good. Let's go to some algebraic operations on vectors, like adding vectors. How do we do that? Geometrically, we have what? I'm starting at this point and I'm gonna graph a vector. I'm gonna call it U, starting at the point A to the point B, and then I need to put the second vector that I want to add to the first vector, and this vector I'm gonna call it V, to the end point of the first one, and this is the point C. So the vector AB, I'm gonna add it to the vector BC, okay, and I'm gonna get the vector AC. Where's the vector AC? Is right there, and this vector would be U plus V. Okay, so actually U plus V would be what? Would be the addition of these two vectors. And how do we get that? We are gonna place the tail of V on the head of U, and we're gonna form a triangle. And this side of the triangle would be the addition of these two vectors. Okay, we can also visualize it, in a parallelogram. Okay, so how do we do that? We are gonna say that I have the vector U, for example, then I have the vector V. Okay, this would be the addition, which is U plus V. Okay, and I told you before that we can place the vector at any different point, but we should follow the same length and the same direction. So this vector that is exactly parallel to this vector with the same length would be exactly V, and I have the same vector U in here. So I have a parallelogram, and this side of the parallelogram would be the addition. So as you see, based on that, I have U plus V, which is this one. This vector is exactly V plus U as well. So V plus U. And since these two are the same, U plus V is equal to V plus U. So we observe that opposite edge is the same vector. Okay, now component wise, if we have a vector u with the components u1, u2, and then u3 in a space, I'm going to add it to the second vector, v1, v2, with the components v1, v2, and v3. Then the addition vector would be u1 plus v1, u2 plus v2, and u3 plus v3. Very good. Okay, so that's addition of vectors. Then I'm gonna talk about multiply by scalar. So let me write scalar multiplication. And what do I mean by scalar? Scalar is just a number. Scalar is just a number. Okay, so for example, if you have a vector u, then the vector 2u would be exactly in the same direction, but twice with the length that is twice as u. And for example, 1/2 u would be the same direction but half of the length of u. How about negative u? Negative u would be exactly the same direction, exactly the same length, but in the opposite direction. It should be parallel to u as well. So this is negative u, but in the opposite direction. So component-wise, you're gonna component-wise, if we have a scalar a, just number a, and I multiply it by a vector with the components u1, u2, and u3, it's the same as multiplying this number to each one of the components, u1, a, u2, and a, u3. Let me show it to you this page of the book. And so in R2, if we have a, b, we have a vector starting at the origin, and this is the end point. This is the same as the space. At any point with the components a, b, and c, we have a vector starting at the origin. Okay. Then we're gonna go to this part, and we're gonna show that if we have a vector 2, 1, okay, starting at the origin, we get the vector 2, 1. You can put the vector 2, 1 at any place, starting at any point. For example, if you put the same vector at the point 4, 2, we're gonna end up at a different point, but we have the same vector, the vector 2, 1. Okay, and if we put it in here at the point 8, 0, the same vector, we're gonna get into different place. And then that's the addition of two vectors. If we have a vector a, the vector b, this is the vector a plus b. If we have a vector a, 2 times a would be the length is twice as a, but in the same direction. The vector a, but for example, negative 2a would be the length of the vector would be twice as a, but in the opposite direction because we have a negative sign. Okay, good. Let's talk about the magnitude of every vector, or basically the length of the vector. So magnitude, if we have a vector u, for example, we're gonna see what is the length of u. So if the vector u has the components a, b, c, then the length of it, or the magnitude of it, would be square root of the square of each of the components, the summation of the components. A squared plus b squared plus c squared. As an example, if the vector u is, for example, negative 1, 2, and then 3, then the magnitude of u would be square root of negative 1 squared plus 2 squared plus 3 squared, which is 9 plus 4 plus 1, 14. Okay, then one of the most important vectors that we are going to use a lot, they are unit vectors. What do I mean by unit? Unit vectors are the vectors where the length of them is equal to 1. And these are in the direction of x, y, or z axis. In the positive direction, actually. So if this is x-axis, this is y-axis, and then this is z-axis, then I have, so this is 1, the vector that I have in here, I'm gonna call it I, the length is just 1, and the vector that goes in here, I'm gonna call it j, and the vector in the positive z axis, in the direction of positive z axis, with the length 1 would be k. Okay, so I, the unit vector I, has the components 1, 0, 0. J has the component 0, 1, 0. And k has the components 0, 0, and 1. Why they are important? Because we can show any vector u with the components a, b, c as the combinations of these. How? I'm gonna say a times I plus b times j plus c times k. As an example, for example, the vector 1, 2, 3, I can write this as 1i plus 2j plus 3k, and then you can check. 1i would be 1, 0, 0 plus 2 times 0, 1, 0 plus 3 times 0, 0 and 1, and so this vector in here would be 0, 2, 0. This vector in here would be 0, 0, and then 3. Now add them up componently. You get 1, 2, component-wise. 1, 2, and 3. Let me show you the unit vectors in here. Oh, actually, so this is A. This is the vector B. The subtraction of the vector is important because I have A, the vector in the same length as B, but in the opposite direction would be negative B. And if I put negative B starting at the end of A, then I can add A plus negative B and I get A minus B. And using the parallelogram law, A minus B here would be exactly A minus B here, this vector in here. And these are unit vectors. 1, 0, 0, 0, 1, 0, and 0, 0, 1 would be unit vectors in the direction of each one of the axes. And on the next video, we're gonna see how we can have the dot product or cross product of vectors.